Hello and welcome back. Today some further maths integration, possibly enrichment. I'm going to write a few integrals on the board and just see what they all have in common and then generalize. So suppose we had to do the integral of 1 over x squared plus 2x plus 5 dx, or the integral of 1 over, let's say, 3x squared minus 7x plus 10 dx. And let's put one more, nice and simple, this last one, x squared minus x plus 1 on the denominator again, 1 dx. Okay, what do they all have in common? There's some quadratic reciprocal, quite clearly, 1 over something. Is there something special about the quadratic? Well, it looks like the first term, the quadratic term, is always positive, possibly. The x bit, plus, minus, minus, can't see anything. The last bit is always a plus by the looks of things, plus, plus, and plus. So maybe we can say some kind of reciprocal with reciprocal quadratic, where the quadratic term is always positive and perhaps the constant is always positive. We wouldn't be far off there. Actually, what I'm trying to create in there is, of course, a reciprocal quadratic where the coefficient of x squared is positive, just to make things easier, I suppose. It doesn't mean necessarily need to. It's just that if we're having limits, we can always get a positive area because we're going to be above the axis. And this is not actually the case of whether this is always a plus. It's a case of this particular quadratics having a negative discriminant. Okay, so they will integrate to some arctan of some sort. So if you have something like that and you had limits, let's say from minus infinity to infinity, these type of graphs, they all kind of look like something like that because they're entirely above the x-axis. This particular quantity, some kind of quadratic like this, when you reciprocate it, it will look like a Gaussian, but it's not really. It's got similar kind of shape, something like that. Where is the location of this particular peak? Well, if the x bit is positive, it will be to the left of the y-axis. This one will be to the, so this particular one has minus 7x. It will look something like that, perhaps. Okay, so we're going to do it with a definite integration, and rather than finding any of this, which of course they're not that difficult to find, we're going to look at a more general problem. We're going to actually try to find the integral in terms of a, b, and c. The minus infinity to infinity, we're going to stick some limits in there, and we're going to say, what if we had a general expression, of course, 1 over ax squared plus bx plus c, there's r dx, and of course we're going to write the conditions that we require for something like this, as we described them a minute or so ago. We're going to say that so we have a positive area. Let's say a is always positive, and of course, otherwise you'll be breaking to partial fractions, r tangencies, and all sorts of other little things. We want the b squared minus 4ac of this particular quadratic to be negative. Okay, so we cannot split into partial fractions over the real numbers. Okay, let's do this particular attempt. So what we're going to get is we're going to get a formula which will have a, b, and c. So all of these three integrals that we just put up there, if we put in the formula the a, the b, and the c, we'll have an answer straight away. Okay, where do we start with this? Well, quite clearly, I won't even start with the integral. I'm going to complete the square. Okay, because from our experience, when we're having irreducible quadratics on the denominator, these go to arctans. Okay, so let's complete the square. So at the moment I'm just looking at the denominator. Ax squared plus bx plus c. It's the same procedure required for when you're deriving the quadratic formula. Let's factorize an a out. We're going to get, of course, x squared plus b over a lots of x plus c over a. Then we're going to complete the square inside the square bracket. So it's going to be x plus half of this, which is b, over 2a in another bracket all squared. And now I'm going to subtract minus b squared over 4a squared. And of course I got the plus c over a. This a, of course, I can times it in now, but I'm going to leave it outside throughout this particular operation, because when it comes to the integral, that 1 over a, I'll be pulling outside the integral, so I want it like this. So far so good. Just need to do a little bit of a tidy for this. So it's going to be a, actually let me do the tidy here so I don't have to go too far down on the board. A x plus b over 2a all squared. And if I put it on, so we have the same denominator, we're going to have, of course, a minus b squared over 4a squared plus multiply top and bottom by 4a is going to be, of course, 4ac over 4a squared, which is my discriminant appearing on the numerator of that. And further tidies, x plus b over 2a all squared. And if we write this now on the same denominator, we can actually write this as, let's put the plus at the front. So we're going to have 4ac minus b squared. So I wrote this bit first, minus b squared over 4a squared. And let us note, since b squared minus 4ac is less than 0, then quite clearly 4ac minus b squared must be, of course, positive, because this is what I've got in here. So this is a positive quantity. I can actually take square roots if I wanted on this particular one. And perhaps to make my life a little bit easier here, because it's going to be a bit of a mess, I'm going to say little triangle. It's a standard way of writing the discriminant. It's, of course, my discriminant dot dot dot. So I can actually say my discriminant is less than 0, so that's that line here. So this is, of course, the negative of my discriminant up there. If you look at what this is of course the other way around. So this I can replace with minus a little triangle. So, and when I get to the end, of course, I will put my b squareds. It's going to be a mess otherwise carrying it all the way through. So I can actually say this is definitely equal to a bracket x plus b over 2a all squared, and I can write now plus the negative of my discriminant, okay, over 4a squared. Okay, so at the moment this is the negative of my discriminant, which is in fact positive. So I can actually take square root. So this particular one is actually a positive quantity. Keep that in mind, because it's a little bit confusing if we do it in general form. If you add numbers, of course, it's very easy to see what's going on. Okay, so although there's a minus here, this is, because the discriminant in itself is negative, this is in fact a positive number. So now we're going to look at our integral. So second stage, we're going to rewrite our integral from minus infinity to infinity. Oops, let's join them together. Okay, and I'm going to write straight away, this is my denominator. I hope I haven't made any silly mistakes, as per usual. It's going to be a square root x plus b over 2a all squared plus the negative of my discriminant over 4a squared. That's my denominator, of course. 1 over dx. Okay, quite clearly this 1 over a, I'm going to move outside the integral so it doesn't really interfere, it doesn't bother us in any way. Minus infinity to infinity. And of course, this is a positive quantity, and this will go to an arctan. Like if you had some numbers, it actually is very helpful before you attempt this, just so you can follow it, to actually perhaps put some numbers in there, that sensible numbers, so you can actually identify what is going on with like something that you can associate with beta, and then look at the same time the integral, of course, in general form. So I can actually say now, I pull that 1 over a, so I can write this denominator as x plus b over 2a all squared, plus I'm going to put another bracket here, all squared, which of course is going to be the square root of, and remember why I said this is definitely a positive quantity, minus discriminant over 4a squared. I'm writing a little bit small, and I hope that it is visible on the video what I'm writing in here, because my handwriting is not that good at the best of times. Okay, we're at the enrichment level at the moment. We're not obviously first timers in this type of integration. I'm not going to be putting a substitution, u is equal to x plus b over 2a. We should be able to see this is the arctan of this, and remember what the form, I'm going to write it here, so we can compare it and we can follow it. If we have 1 over, and I'm going to use a u, and for the constants, normally in the formula booklet it'll be a squared, but I'm going to use a k, so because the a here means other things and it's going to be very confusing. So this particular integral with respect to u, integrated with respect to u, will be 1 over k, the arctan of u over k plus c. So this is the answer, equal, downwards, vertical, equal, for something which looks like that. So if we begin our integration, I'm going to put it there. We're not going to worry about the limits for the time being. We got, of course, the 1 over a. This is outside the integral. And we're going to need from this side here the 1 over k. What is the 1 over k? The 1 over k is 1 over this quantity here. So it's going to be times, I'm going to move it outside the evaluation brackets, and I'm going to write it as the square root of the negative of the discriminant. And I'm going to take the square root of this quantity, because that's a perfect square, is of course going to be 1 over 2a. Just make sure you follow what this is. This is from this formula, I hope I'm not in the way, the 1 over k. This is the k squared there. Okay, now I'm going to put my evaluation brackets, because we've got limits, don't forget. And this is going to be the arctan of u. This is my u, so that's the arctan of x plus b over 2a over the k, where k is of course again the same thing, over, looks very scary all of this, doesn't it, over 2a, close the argument of the arctan, and let's put minus infinity to infinity. Let me just do a tidy, just it's not really necessary, but if you look at this particular term, multiply tops, multiply bottoms, the a and the a here will cancel, and we got 1 over a half, so it's going to give us a 2 at the top, over the square root of the negative of the discriminant, and the arctan, which is going to be arctan. I'm going to multiply this to the top, so it's going to give me, think of it as multiplying top and bottom of this fraction by 2a, so it's going to give me the arctan of 2ax plus b over the negative of the discriminant. Hope I've done it correctly and I haven't done any mistakes there. Let me just double check this bit, although it won't matter really because of the limits. It's nice not to make mistakes for once. So 2ax plus b, and of course, yes, I'll make it correct. And we're ready now to evaluate this. I'm going to rub off the top where I manipulated the denominator when I completed the square. And I'm not going to go through a formal limiting process. I'm going to be very sloppy with my workings from here. So this is now going to there. So this is going to be 2 over the square root of the negative of the discriminant. When I put infinity for my x, this becomes infinite. The arctan of positive infinity is, of course, pi over 2. Minus, when I put negative infinity for my x, this is the arctan of negative infinity, which is minus pi over 2. So if we simplify this, that's going to be just simply pi positive. So we're going to have 2 pi over the negative of the discriminant. And of course, I now have my general answer, or it's a formula really. And what is the negative of the discriminant? The discriminant is, of course, b squared minus 4ac. The negative of it is just swapping it around. So it's going to be the square root of 4ac minus b squared. This is the desired result. I think it's very beautiful. It probably looks more complicated than it really is. It's just a lot of tedious things, just keeping your head together. I remember when I first saw the proof of the quadratic formula as a youngster, perhaps I was at O level at the time, I thought to myself, oh my God, you know, there's a lot of stuff, how I'm going to keep track of it. But it's not, it's just loads of letters. Just take your time, and it's not as bad as it looks. And something came to my mind now, and I'm going to try to remember to put a link on this video. I'm going to do for the undergrads exactly the same thing, but by contour integration. I'm going to put a link on that video as well for this particular video, and hopefully I'll get the same answer by university techniques and complex integration. For the time being, who's laughing now?